This is the website for the American Board of Criminalistics. It is a certifying body for board certification of criminalists. I am board certified with ABC. I took the test in like 1997, I think. Oh yeah. At any rate, there's like a really good chance now that we will offer the certification sitting in early June. It is not for everybody, partly because it'll cost you $300 to take the exam. Exactly, and you know it's John Jay College. We don't have funding to, pay for it for you. However, and it's the it's the 300 split into a $50 basically like administrative fee, and then a $250 fee for the sitting. And it's refundable. The $250 is refundable if you can't make it for some reason. The $50 is not refundable. All that's like on the website over here. Why is it so expensive? Well, part of it is administration costs for the sitting, but they also do a background check on each person who applies to take the exam. Okay. So why would you want to get board certified? Board certification basically is an added layer of professionalism to show that not only do you know what should be known for the specialization that is being tested for, but moving forward, when you do get board certified, it shows in order to maintain the certification, you need to be active in the field of interest. So before we get on to when you get board certified, the test itself is very challenging and it's expensive. It's I think at least a 3-hour, we allot like 3 or 4 hours for it because part of the time is administrative. Get everyone seated, everyone gets a bottle of water, we read instructions about how you can't look any way but up or down on your paper. If you look side to side, we can say, okay, you get out of here. I know it's really, really intense. But on the other hand, I guess it's not that much different from one of my exams. Well, anyway, so I am working with Dr. Diachuk to offer a sitting. I've already had Dr. Prince send an email to the grad students, and I have about 4 grad students who have said that they will do this. It's enough for us to offer the sitting. Dr. Diachuk and I will proctor that exam. And I think that less than 50% of the people who take the exam pass. Okay, passing grade is 80%. If you pass or fail, they don't tell you what your grade is. Okay, they just tell you that you've passed, and you're like, yes, that's great. Or if you don't pass, they will typically give you an indication of what you would need to study more of in order to pass the exam if you choose to take it again. But like I said, board certification is one of the things that was recommended by the National Academy of Science in the 2009 report about how there's so many problems in forensics. There's people who get hired to just testify about whatever the lawyer wants them to testify about. There are a lot of problems in the field. So board certification is an added layer of professionalism, which many people feel would improve the profession, although right now it's not required for criminalists or expert witnesses to be board certified in order to testify in a court of law. But a lot of people feel that that would improve the quality of testimony in courts of law when it comes to testifying about physical evidence and analysis and results and conclusions. From the perspective of the potential employer, if you have passed that exam, that looks pretty good. If you have on your resume, and for you guys, you would not be board certified if you pass the exam right away, because you need a 2-year experience in order to be fully certified and become a diplomate. If you pass the exam, but you don't have those 2 years of full-time experience, then you're an affiliate, which means you're certification eligible. You're not certified yet. And so basically, and this is what, this was my experience with it. I took the exam in 1997. I was a student. So I was an affiliate, a student affiliate, or not even, just an affiliate with the American Board of Criminalistics. As an affiliate, each year I would supply the same documentation as other diplomates in order to maintain their certification, which would mean I would have to fill out paperwork indicating that I had attended meetings, perhaps had taken training courses, perhaps had trained other people, perhaps had published papers and that sort of thing. All those things would show that staying current in the field, and that's what we want for people who are in criminalistics working in laboratories. So for you guys, and then when I had my experience, and they include education, I submitted paperwork to the ABC to become fully certified as a board-certified criminalist. Test has changed over time. There's information here, and you could read, get the application. If you're interested, I want to know pretty soon. However, I will, once Dr. Diachek and I have hammered down the date that it will be given, and ABC has the information and is able to say, okay, there's this exam sitting at John Jay College, most likely in this room, first week in June with the specific date. If you want to sit for the exam, you have to send in your application with the 2 checks, one for $250, one for $50, a minimum of 60 days prior to the sitting date. So the deadline will be early April, which will be 60 days before early June. Okay, so you have a few weeks to think about it. In addition, so the application needs to be filled out, 2 checks. There's also a form for a sitting, which would be, I want to sit for the exam at John Jay College on this date. And you need 2 references. So all those things could probably go, oh well. The references are sent individually by whoever you asked to be a reference for you. The other things can be sent postmarked by the deadline, or the 60 days prior to the sitting date. So, like I said, I want you guys to think about it and come and talk to me if you're interested. I think it's a good thing for the field overall, but it's a challenging exam, and I would completely understand $300 is a lot to invest, but it's an investment in your career to some extent. And it's not, like I said, less than half the people pass the exam. So it is not easy by any means. That said, I do have some study guides and materials. And they are on Blackboard. They're in the course documents section, I believe. And it says ABC GKE study materials, because years ago, the first exam anyone would take would be called the General Knowledge Exam, GKE. The philosophy of the American Board of Criminalistics is that you should be a generalist and have a good understanding of a variety of different evidence analysis. And then many people move on to have a specialty. They do drug chemistry, they do paints and polymers, they do hairs and fibers, and that sort of thing. And if you wanted to, you could take another test in that specialization and become a fellow of the ABC. And in addition to your annual paperwork, you would also have to take a proficiency exam, typically within your lab that you worked in, and provide the results of that in order to maintain your fellow status with the ABC. They changed things around, so now they only have a single exam to become a diplomate. You guys would be, I think your best option would be the Comprehensive Criminalistics exam, okay, the CCE. So, but there are other choices. I think one of the grad students who had experience, a couple of years experience doing drug chemistry, is going to choose to do the drug chemistry exam, which makes sense. So those are some things to think about. And the this is from a web page. I think if I go backwards, which is no longer active. study guides and review questions came from an online GKE workshop given several years ago by the National Forensic Science Training Center for the Phoenix Crime Lab. So those were publicly available, and I just saved them as PDFs. And it's no longer available, but you know, like I said, it was publicly available before, so they can still serve as study guides. And your DeForest, Gainsland, and Lee textbook from FOS 313 is an excellent resource because it has basically an overview of all criminalistics, including things I didn't teach. So it's a good thing to use as a study guide as well. I recommend people get together. If you want to do this and you're committed and you feel prepared for it, then you get together and have a study group. And you go over this stuff, you go over the grade book, you ask questions, answer questions, you come to me, that kind of thing. In the past, the elder Nick Petracco, who is one of our Monday instructors, I will have to ask him, but he's given a study session as well. So, once again, I spent enough time on this, things to think about, and come and talk to me if you, yes?
So that's the first time that you're offering the test at John Jay?
No, we've done it, this will be like maybe the 4th time, I think.
Oh.
We offered it in 2016 here. I set up 2 exams in the early 2000s. So yeah, this will be I think at least the 4th time, maybe more, that we've offered the exam here. Our success rate is not bad, but that usually means a few of the people out of the many who take it pass the exam. Okay, so you know, like I said, I wouldn't push you to take it if you don't feel ready. The flip side of it, I guess a little bit more history. When this exam, board certification, was first put together, a lot of lab heads thought this will be excellent. I'll get all my people board certified, and then we'll be like super lab, you know, people will come to us and all that jazz. And then, I mean, you know, that was a thought process. They had their people take the exam, and a lot of them failed. Yep. And why did they fail? Well, part of it was, let's say you've been working in the crime lab for 15, 20 years, and you've just been doing your one thing, fingerprints, drug chemistry, and you don't remember the stuff that you learned in school if you started off in a forensic science program, general knowledge. And like I said, one of the platforms of ABC is that criminalists should have general knowledge, which doesn't mean you have to know everything about every single type of evidence analysis, but you should have general knowledge. And then it would make sense you'd have specific knowledge in the discipline that you're working in. So a lot of people failed. They didn't have general knowledge. Lab directors were like, oh, okay, that doesn't look good. Let's rethink this moving forward. So the philosophy might also be that as students, a lot of this stuff is fresh in your memory. You know, if you move on and you're, like I said, you're working 5, 6, whatever years in the lab, the greatest likelihood is you'll be focusing on the drug chemistry, the DNA, fingerprints, firearms, that sort of thing. And some of this other stuff is going to be, you know, becoming more cloudy in your memory. But that does, like I said, it's not an easy exam, and I'm talking to you guys about it in terms of what's good for the profession, what's good for careers, but I don't want you to plop down $300 and then end up with you know, it's a lot to invest. So this is more informational than pushing. But just to let you know, you'll have that opportunity because we will offer the exam in June. We've had enough feedback that we will offer it.
Okay, so like you're offering it in June. June seems pretty soon. But it's possible if you're really willing to invest the time. Are you guys planning on doing this like more regularly, like maybe once a year, or is that the goal?
I don't know if once a year is going to work in terms of getting a good number coming in. And just to let you know, we will be inviting other agencies. So I think last year, 2 years ago when we offered it, at least one person, maybe 2 people from outside labs came to the sitting here, just because it's convenient for them. NYPD will invite them. one of the grad students who graduated, passed the exam in 2016 and is currently working at NYPD and feels real proud about it. So she was chatting with coworkers who were also interested in taking the exam. So she said, yeah, definitely tell us if you're offering it, because I know people here who want to take it. And New York, it's easier for them. The exam is offered at the NEAFS meeting every year. It's offered at the Academy meeting every year. And then there'll be sittings throughout the country, but you know, New York, you guys show up here anyway. You know what I mean? So there's an implication here that it's a little easier for you to, you know, take the same subway ride or whatever ride you take to get to John Jay College, as opposed to, oh, it's in Anaheim, California next year, or it's going to be in, you know, like I said, those are not necessarily convenient for you guys. So come and talk to me. Definitely, if you're going to be taking the exam, you'll probably need a reference from maybe me, maybe somebody else that you've done well with at the college. So come and talk to me anyway. Any other questions?
Question. If you take this multiple times, can employers see that you failed the first time if you fail?
No. You would not advertise it on your resume, took it and failed.
Well,
You know? just like you wouldn't write down organic chemistry or whatever. I got a D, sorry, you know. You don't put those things on your resume. The things where it comes into play in your career, one of the reasons why they don't tell you your grade is because they don't want lawyers to use that against you when you're testifying. They don't want there to be, oh, I hear you just barely passed that test. So maybe one question and you would have failed. So how do we know that you're really, you know, an expert and blah, blah, blah. You know, I mean, like I said, so they don't want your actual grade to be used against you when you're testifying. So you passed, you're certified. If you don't pass, then I don't necessarily know if it's a public record that you took it and didn't pass. Like, how would a lawyer know that? You know what I mean? But I don't know for sure. But yeah, if you do pass, then like I said, that's an excellent thing to put on your resume, because like, oh, the person knows stuff, you know? They passed a very difficult exam, and it would look good to have more certified people on my staff, you know, as lab director, that kind of thing. So, yeah, it's a good question to think about, though. Yeah, they would not know if you took it and didn't pass. There's no need for them to know that. Any other questions?
When is the wood lecture? Because a few of us thought it was today.
Oh, yeah.
Oh, really? Okay, is that on the
That's why
schedule?
Brianda was on time.
I don't know, but
Yeah,
I just.
where'd that come from? You guys
Well,
They were talking about
talking,
it.
and then we were like, "Is that today?"
I know that Franny has been preparing things. I'm waiting to hear, and maybe you guys know more because I'm not always in the lab. Is the wood exercise ready to go? Are there standards and unknowns? If it's not, then I'm not going to have Dr. Dycha come in.
I get it. You want us to be like.
Yeah,
on
it makes a
lab.
lot more sense for him
Yeah.
to come in and talk about it, and then you're like, yeah, I'm all ready to go into the lab and do this, you know?
Yeah.
As opposed to, oh yeah, he gave a lecture like a month ago and I forgot everything, and now, right? So he's already talked to me. I don't know, you probably don't know Dr. Dycha unless, I don't know. He's our firearms guy, but he's also, you know, done a lot of work with wood identification, so he'll come in to do the lecture for that. I'll talk to him again, but like I said, I'm waiting for the lab to tell me, yeah, wood exercise is ready to go, and if it is, then it makes more sense. You learn about it, and then, you know, you go and do the exercise. Okay.
I did have one other question about the test. What is the format of the test? Because I saw the practice stuff you posted, and some of it was multiple choice, and then there was
Are you
like,
talking about the American Board of Criminal
yeah,
Justice?
then there was like essay.
It
or
is, no,
discussion.
it is only
There's
multiple
essay
choice.
questions like to think
It's
about.
kind of like, in terms of like comparisons, it's not like the SAT, but like the SAT, there are many questions, and there are also a few experimental questions which will not count towards your grade. They just kind of throw it in there to see how people do and make decisions about that. About, okay, we'll use this question in the next exam, that kind of thing. So most of the questions, but they're multiple choice. I'm not aware of there being any essay question.
Because on the practice thing that was there was like a discussion and like a essay thing that you're supposed to like discuss with the group. And I don't know if that was like just for a
Study
workshop
group?
exercise
Yeah,
or if
probably
there was
workshop
like,
exercise.
yeah.
Yeah,
It said,
I will talk to
yeah.
Dr. Dychuk, who's on the board for ABC, but I would be highly doubtful that they have incorporated an essay like the SATs do.
One of the things
Partly
that
because
500
it would
words.
be onerous
Yeah.
to grade that in an unbiased fashion,
Yeah.
and they would have to be concerned about stuff like that.
Yeah, it said
So it's a
500 word
multiple
essay
choice
on.
exam. You'll get like a sheet, just, like a larger version of the Scantron sheet. And you darken the answers, number 2 pencils, that kind of thing. So we didn't get very far with species. Is anyone ready for that?
People are doing checkouts right now.
Yeah.
All right.
Not me.
Not me.
Some people.
Not me.
There's at least
Okay.
3 people.
No, it's good. I would be cautious if, one of the reasons why I did the hair lecture at the beginning was because I wanted you to have at least some mental exercise with it before you actually did the exercise in lab. But some of you, really ahead of the curve, and you're already doing exercises I haven't talked about yet. So if that's the case, then you make sure you want to read up about all these things, you understand things well, and I guess that'll help you pass checkout as well, right? Pre-check. So I think last time we've gotten this far talking about biological specificity because we're trying to answer that question. If I have something that is a blood stain, and I know it's a blood stain because I've already tested it and got confirmatory results that there's, heme there from Takayama or Teichmann results, then how can I know that what kind of animal it came from? So we're not even talking about individualizing to a single living thing in the world, like it's from this dog, Fluffy, or it's from this cat, Jones, or whatever you want. We're talking about looking at it from a species point of view. Okay, what would be common in humans and or primates versus what would be common in all cats, which would also, in science, there's error, right? So whenever you choose a particular kind of analysis to do, a test to do, there may be occasions when there's a sample that doesn't give you the expected result because there's a mutation, or there's something weird, or the person has an immune disease and they don't have what you would expect in their blood because of these kinds of issues. But you do choose a test which will work most of the time because it'll give you useful information when you do that test on that sample. So biological specificity, knowledge of how various species can be differentiated based on their biochemical differences. So we're looking at species-specific protein differences. You can try other possibilities, but that is typically the approach that's taken for figuring out. It's a reddish stain, I know it's blood, but what kind of animal did it come from? Okay, so immunological methods are used, and that's back to the idea that we already had some thought with about antibodies and antigens, right? Because we did that with the ABO system. The antigens that are on the surface of the red blood cell are agglutinogens in the ABO system. There's the A material, there's the B material, and there's the precursor O material. And as we learned from a few people who had sent me information, that the differences are, well, part of it was the A1, A2 stuff, but their differences are in the sugars that are added to the precursor substance. Okay, so you can have type B blood, and in your serum or plasma you'll have anti-A. So back to that, thing, and you guys kind of saw that with the homework that you did that was due. I guess it'll be due. I guess I shouldn't make it due in the middle of class, right? I just realized that I had to do it, noon today. I'm like, wait,
Did you said 12. I didn't know if that meant midnight or noon. Like,
I don't know.
so
1200, 1200 would be noon, right?
So what's 12 a.m. then?
0.
Oh.
And it's unlikely that I'll ask you to submit something at 0 hours, you know. Okay.
Dumb.
All right. So we're looking at this idea of using a reagent, which would typically be some kind of antibody, or I'll talk about polyclonal or monoclonal, a reagent, an antibody, to recognize a particular antigen. And antigens are interesting things because antigens can be pretty much almost anything that your body defines as not from me. So it could be antibodies from another human being, not from me. I'm going to make antibodies against those things. It could be materials from other animals. It could be the viruses that people sneeze into the air and you're breathing it in. Now you've got a cold, but now your body's making antibodies against those antigens. As my first example mentioned, an antigen can be antibodies that are foreign to you. So it's actually defined by the person, which is the same reason why you can get a transfusion of your own blood and it won't be any problem because that's from you. Your body actually has biochemical markers to recognize things that have come from you versus things that did not come from you. And of course, that'll make, we talked about blood transfusions, but people have kidney transfusions, people have heart transplants, people have all kinds of situations in which they're getting a donor, they have a donor providing them with an organ, for instance, that your body might reject because your body will see, hey, don't see the markers that show it's from me, so maybe this isn't a good thing for me, and rejection of the heart that was transplanted into you, or rejection of whatever possibilities. So we're going to be talking about immunology in more detail with the species of origin testing. Okay. So the Uhlenhuth reaction. In 1900, Uhlenhuth was concerned or interested in species of origin detection, and so he developed the first immunological test for determining species of origin for blood stains specifically. One of the things I don't think I talked about as much in the last couple of lectures is, but it should make sense, the approach in analyzing a liquid bodily fluid, let's say there's a pool of blood on the ground, so you have the potential to collect some of the liquid in a test tube and analyze that, versus, oh, it's a dried stain on the wall, on the floor, on some article of clothing, on a shoe. Dried blood does not have the same characteristics clearly as liquid blood, and so approaches can be different when it comes to those situations. So we also want to think about the idea that, okay, if we came up with a test, but we needed actual liquid, fresh liquid blood, it's not going to be helpful for a lot of forensics where the sample we get as evidence is a dried stain. It might be a few weeks old, it might be months old, it might be a few years old, okay, which also adds complexity to that situation. So known antibodies, which we'll call precipitants, are used to precipitate the unknown antigens. So he created a precipitant test, and precipitant is kind of what it sounds like when you add the reagent in liquid form to the unknown, which is typically a liquid extract of the blood stain. So 2 liquids, then you'll get precipitation. Okay. So it's not quite, we're not doing like microchemical crystal tests with this, but we're looking for a white precipitation, and I'm going to talk about a few different ways of looking for this precipitation. You guys will end up doing it in the Ochteloni method. So it's a gel, yeah. I was like, oh, Ochteloni, it's like a German word, and it looks like Ouchteloni, ouch. Right? the basis of this, an antigenic substance from one species, like humans, can induce the production of antibodies in another animal if the foreign substance is introduced into the second organism's system. So the antibodies produced by that other organism are specific for the antigenic substance. What does this mean? What it means is that if I were to take human serum, so you could take, get blood out of someone's arm, let it separate off, you got the serum at the top, take some of that serum and inject it into, let's say, a rabbit. Okay, the rabbit's, system will say, hey, that's foreign, and the rabbit's system, the rabbit's immunological system will produce antibodies against that foreign material that you injected into its circulatory system. So that'll mean that you could take the rabbit's blood now, and typically the rabbit's serum will have its antibodies, and now you have a reagent, because in the rabbit's serum will be antibodies that were made against human blood or human serum, okay? So if you were to take the rabbit's serum that was exposed to human blood and mix it with an extract of human blood, you can expect that the antibodies in the rabbit serum will attach to the antigens that it was made to recognize. And if you can get that reaction to occur in a way that you get a precipitation, then you can get, you have a test. You have a test for human blood. And so you can actually do this for, almost any kind of animal. But the hard part is making a quality reagent, which means, and we'll talk about how do you make a quality reagent. Remember, the factory for the reagent is the animal that you inject it into, right? So the rabbit or the guinea pig or the goat. So for you guys, I think some of the reagents that you'll be getting in your little kit for species of origin will include, let's say, sheep anti-human reagent. And what it means is that a sheep was injected with human serum. They use rabbit, they use a number of different animals, which means, like I said, these animals are the factories for the material that is being, the reagents that are being made. Okay, so that's the situation. And to go on a slight tangent, it's not too different from the vaccinations that you've had probably throughout most of your life. I don't know if any of you are like, anti-vaxxers and bringing measles to everyone here. But basically, for a lot of the time since we've had vaccinations, it's been required. And as a baby, the doctor, injects you with a vaccine against polio or measles, mumps, rubella, all the typical types of diseases, childhood diseases, which killed a lot of kids, in history until people came up with this idea of, you can actually take either a dead form of measles or a modified form of measles or polio or whatever the case is and inject it into the kid, and the kid will begin making antibodies against it so that if they are exposed to measles, they've already have antibodies in their system that will fight it before it can hurt them or give them a bad reaction to it. And if you've had, maybe if you take the flu, if you get a flu vaccination every year, maybe you're like, I don't know, I don't like it because I don't feel well when I have a flu vaccination, my arm hurts, or whatever the case might be. But remember, when it comes to vaccinations, sometimes what you're getting is just a mild form or a modified form of the thing that could be potentially much more dangerous. So back to the idea, they're injecting something into you so your immune system can make an antibody against it. Same reason you don't get the same cold twice, because once you've had it, your body makes antibodies against that virus. And so if you're exposed to it again, you've already got the thing to fight it. Okay. So same idea when it comes to this immunology stuff. Okay. Already here. Immune response on the part of the organism is the same response which produces specific antibodies to certain diseases when disease-producing organisms enter your system. So this is exactly what I was just talking about. And I also mentioned, organ transplants and grafts. Same idea. So if, someone needs a kidney transplant, they will do basically a genetic profiling of the donor and the recipient to see if they match well. So the better the matches, the less likely that the recipient of that organ will reject it. Okay. So immunology is the study of these reactions, antibodies designed to attach itself to the specific foreign substance, forming some kind of insoluble complex. Even in your system, like I said, especially around these days, someone's like sneezing, or they wipe their nose and that's gross, right? But they touch the banister or the elevator button or a door handle, which is all over the place, in subway, hole that you're hanging on to. You don't know what kind of cooties someone had. Touch that stuff. So you're exposed to that. Your body makes antibodies against it, and inside your system, basically these antibodies are attaching to the antigens. They are being removed by your immune system, by your T cells. So you have a variety of different cells that are part of white cells, are part of that. So back to that idea, you go to the doctor, you're not feeling well, they'll check your blood count. If you had a lot of white blood cells, it's an indication that you're fighting some kind of infection. Your body had to make more of those things to get rid of the bad stuff that you inhaled or touched or whatever. Okay. So those complexes are scavenged from the body by special mechanisms, such as being engulfed by a certain kind of white blood cell called a macrophage. So this is a macrophage in action. The bad thing that got into your system is symbolized as a red oval over here. When it gets into the macrophage ingests that bad thing, basically breaks it down, and then gets rid of the detritus, what's left over after it's chewed it all up. Okay. And so part of this is all about, like you get sick and yeah, you're blowing your nose, the mucus, all that stuff is like, oh, it's kind of gross, but yeah, you got to get that stuff out of you. Okay. So the immune response, as you're already aware, takes place inside your body when you're alive, in vivo. Immunological antibody, so I'll use AB to symbolize an antibody. I'll use AG to symbolize an antigen. And I also will sometimes talk about antibodies. For instance, in the reagents you receive in the kit for your species of origin exercise, you think of a single antibody as having a particular structure, and remember I showed you the Y-shaped IgG, and each IgG recognizes a specific antigen. Remember, it has the recognition sites. So you might actually have a little tube that has antibodies that recognize all different parts of the antigen. So it's not like a single chemical species. It's polyclonal. It'll recognize that rhinovirus, but not just one part of the rhinovirus. It'll recognize this part, that part, the other part. Or when it comes to, let's say, recognizing a human blood stain, it'll recognize this part of the human antibody, that part of the human antibody. Polyclonal, it recognizes different parts as opposed to something that's far more specific and only recognizes one thing. Okay, so I will still occasionally refer to like an antibody, but what I'll really be talking about a group of antibodies. Okay, so something to think about. So the antibody-antigen reaction is utilized in the same way to form in vitro to form a visible precipitate, like a white, just like when you mix two chemicals together in chemistry or organic chemistry, and the product was a crystalline material, and you saw that white precipitation or other colored precipitation. The bottom of the test tube, you spin it, you get rid of the supernatant, maybe you wash it a couple of times, and then you weigh how much product that you got, that sort of thing. So visible precipitate in analytical tests to tell me that, okay, it gave me a positive with dog blood, or it gave me a positive with cat blood, cow blood, etc. Okay. Serum of host animal containing the antibodies is used as a reagent. So just like I said, they'll inject the foreign material, which is blood from a different animal species, into the little animal factory to make our reagent. So let's go back to immunoglobulins. We learned a little bit about IgGs and IgMs when we talked about blood. Remember the agglutinins that you have in your plasma. That's your anti-A or anti-B, depending on what blood type you have. Those are agglutinins. And those, the ones that are associated with the ABO system, which would be anti-A and anti-B, remember those are IgMs that are decamers. I recognize 10 recognition sites. And I mentioned back in that lecture that you're also testing for the Rh factor. And anti-D is an antibody. It's only, basically, it's bivalent. It only has 2 recognition sites. So it's not as strong a reagent for causing agglutination. Immunoglobulins, that's where you get your Ig from. IgG, IgM. There's actually many different families of immunoglobulins. Okay. So immunoglobulins are found in the gamma globulin fraction of the blood, and that'll be inside of your plasma. Okay. So like I said before and alluded to before, your immune system basically lives inside your plasma. That's where the antibodies that you've been making all your life, that's where they live. Okay. So we've got your AGAs, AGGs, AGMs as just 3 of the many possibilities, but very common possibilities. Okay. And within these subclasses, numerous specificities. Okay. So the choice in your antigen injected into the host animal defines the species selectivity of the resultant reagent. So the question might be, if I want to make a reagent that will recognize human blood, what is it in human blood that's in most human beings' blood that I can put into that animal so they can create an antibody against it? And as I've mentioned before, the thing that can differentiate humans readily from dogs, cats, cows, pigs, all these different possible animals, is the antibodies that are in their plasma. So the antibodies are going to be used as antigens. We're going to inject those into our host animal. The host animal is going to make antibodies against the antibodies. Okay? So, I mean, it makes sense when you think of the possibility that an antigen can be pretty much anything that is injected into the body, and your immune response is, okay, let's make an antibody against that. So proteins which are conserved evolutionarily are not good choices. What do I mean by that? I don't know if you've ever been to like the American Museum of Natural History. I haven't been there in a while, but for a long time they had one hall in which they had this huge evolutionary tree, and they basically show, microorganisms or single-celled organisms that evolved into multi-celled organisms, and then how closely related are we to chimpanzees? It's all part of this evolutionary tree. How closely are we related to like fish or reptiles or whatever? So the evolutionary tree shows at what point in biological evolution do scientists think that 10 million years ago there was this mutation, and then these different animals separated from each other in the tree. And then somewhere along the way, oh, human beings. So the idea of evolutionary conservation is things that are really needed for an organism to survive are typically well conserved, because if you mutate that really necessary thing in the living organism, if you mutate it and it doesn't work, then you don't get a living thing. Okay? As a good example, hemoglobin. Hemoglobin is the gene for hemoglobin. It's not going to tolerate much in the way of mutation because you need hemoglobin. I mean, clearly, right? You need it for your circulatory system to do multiple functions, oxygen carrier, carry away waste, that kind of thing. So if something happened and you got a mutated hemoglobin gene, then depends on the mutation. If the mutation is just a little bit and it doesn't really change the nature of how well the hemoglobin works, then maybe the organism can survive. Okay, but a lot of times, and you've learned about this probably from biology, there's a mutation, there's an insertion, and it changes the whole codon reading system, and now the protein is totally different at the point after the mutation, and you get your protein that is not the same as what it was supposed to be. It's not going to be able to carry oxygen very well. And then, if that's the case, then in utero, the fetus doesn't survive. It's a miscarriage. Okay. So hemoglobin, there are a few different examples, and I'll actually talk about that a little bit later in the lecture, of biochemicals in living organisms which tend to be evolutionarily conserved. So even as different species diverge from each other, they still need this particular kind of biochemical to live. Okay. Not that there aren't mutations, like we talked about sickle cell hemoglobin. Okay. But you don't want to pick a biochemical in a system which is going to be the same in all different species. So we're starting to look for things that there's diversity, and like I said, we don't want to pick things which are evolutionarily conserved, because then we'll see it in the dog, and we'll see it in the human, and we'll see it in the cat, etc.
I don't get what you're trying to say with that statement. Like, I got when you were saying that the things that are most essential, like hemoglobin, like that stays through time, and that's necessary.
So, as an example, I've got my dog blood stain, my cat blood stain, my cow blood stain, and the human blood stain. So I've got these, several red stains from different animals. They all have hemoglobin because we got our test result, the crystal test result. We're not going to choose to find a test to distinguish these 4 blood stains, which animal, based on the kind of hemoglobin, because the hemoglobin tends to be the same among all these things. They're evolutionarily conserved, so it tends to be the same in these different animal species. What we want is something different. That, it's different in cats compared to dogs, compared to sheep, compared to humans. That means evolutionarily it's not conserved, it evolved, it changed, and allowed us to be wonderful. Look at this, right? We're not like these single-cell organisms that are like, just live for like a day or two and then dead, and then have lots of, other single-celled organisms made from you, etc. That's what I mean. So the idea of evolutionary conservation means that many different animals will have the exact same biochemical. We want a biochemical that's different, that in the evolution of different species, these biochemicals became different along the thousands and millions of years or whatever the case may be. So they're not good markers because they'll tend to be the same among different animals. We want things that are different between those different animals. That's the whole point. We're trying to find a test that can distinguish species of origin. Okay. So gamma globulins, that's the thing we're going to be looking for. So as it turns out, these different animals, our immune systems have evolved somewhat differently. So a dog's immune system is a little bit different from, the cow, the human. So the immunoglobulins in these different animals' plasma is going to be different enough that we can take advantage of that, of those differences, to make a test to recognize those differences. Okay. So gamma globulins are the Ig fraction of blood serum. These evolve much faster, which means they change. Evolution is change. Okay. More likely to be useful in differentiating species. And so, interestingly enough, the gamma globulins are antibodies, but if we make antibodies prepared against our antibodies, they will be more specific for a human being. So we're not at the point where we want to find something, because we know that's the genetic sequence, in a single person. What we want to find is what's different in all of human beings versus all of these other animals. Okay. So ABO agglutinins, I've already mentioned, fall into the IgM class. All these are IgG isoglutinins in the serum. So you have all these different things. Okay, the AGMs are one kind of thing that's in your serum, and you might not have those AGMs if you're type AB, right? AB blood, you don't have anti-A, you don't have anti-B. Remember that was from earlier on. You can't, because then you'll have agglutination of your blood cells in your own circulatory system. and that doesn't make sense. So you've got IgMs, you've got other IgGs, you've got some IgAs. So these are in your saliva, in your circulatory system. I already mentioned a couple of lectures ago about how the IgM class is more effective because it's got 10 recognition sites. IgGs only have 2 recognition sites. And I showed you the image of how an IgM looks like a pentamer, or 5 of these kind of, arranged in a very pretty structure. Okay. 10 receptors per molecule. Same thing as before. Okay. And once again, this is what I was talking about. That this is a receptor, and this little cartoon diagram, you already know that this is representation for a biochemical. Okay, so this is talking about amino acids in a chain that take this particular form, and they use this Y shape to designate an antibody, but it's not like you have little Ys. They're composed of proteins, and the receptor site is able to recognize a specific portion of the antigen that it was designed against. So the precipitin test, the reagent, which we'll call an antiserum, is produced by injecting the desired antigen into a lab animal. It could be a rabbit, could be a sheep. There's a number of possibilities. The injection sequence is usually repeated several times. That's kind of like booster shots. Like if you get hepatitis, vaccinated against hepatitis B, you got to go 3 times, right? The first shot, a month later another shot, and then a year later another shot. So the whole idea is, first, if we only inject you with the anti-hepatitis B vaccine once, probably not going to make enough antibodies in your system to be able to fight a hepatitis B infection if you're exposed to it. But if we do this 3 times over the course of a year, then you're more likely to produce more antibodies and have an effective immune response if you're exposed to hepatitis B. So it's a similar idea. You inject that rabbit once with some human serum, and maybe it makes a few antibodies, but if I were to take some serum from that rabbit now, it might not be strong enough as a reagent to be able to detect human blood, okay, human serum. So animals in the laboratory, and maybe after a few weeks, you give it a booster shot of human serum. And then after another couple of weeks, another booster shot of human serum, and that poor animal is like, oh, I'm making lots of antibodies against this human stuff that's being injected into my circulatory system. Okay. So this is the idea of producing a high titer. So we're going to talk about what titer is in a little while. But basically, it's a measure of the effectiveness of the antibody. That's one way of looking at it. Titer can also be used to apply to understanding antigen concentrations as well. Okay. The serum of the host animal is used as a test reagent, and you don't have to sacrifice the animal. You're basically getting a blood donation from the rabbit. And just like human beings, I don't know if they give the rabbit orange juice or what, but they continue to feed it, give it nutrition, and it makes more blood. And it's your little factory for making your reagent. So maybe after a few weeks, you could take some more blood out of that animal, that rabbit, and separate out the serum, and then sell it for a lot of money to John Jay College, so everyone here can do their species of origin testing. Okay. So reagent serums of varying degrees of specificity can be produced. It's better if the antigen preparation used to induce the antibody production is as pure as possible to begin with. But what does that mean? Like, which human? The reality is, I'm different from you in terms of what I've been exposed to in my lifetime, what antibodies I have in my plasma and that sort of thing. So when we're talking about purity of the antigen that we inject into the host animal, there's a few different options for how we choose to make an antigen that will be injected into a host animal. Okay. So as pure as possible. You can improve the specificity of an antiserum by absorbing out unwanted reactivity. So basically, you injected the animal, the rabbit, let's say, with human serum, but when you tested it to see if other animals would also give you a false positive, for instance, and you see, oh, occasionally, I don't know, this other animal will give me a cross reaction. It might be possible to absorb out that reactivity, meaning that I've got my serum from the rabbit's been injected with human serum, okay? But there's a reactivity that I don't like, so I'm going to expose, not that it makes sense, but let's pull something out of the air. Let's say occasionally a chicken, chicken blood will give you a positive result, even though you made this reagent to test for human blood. So what's up with this, chicken thing? So if you expose, sometimes if you can absorb out, expose the antiserum to the other contaminating material, or not contaminating, but the unwanted reactivity, and those antibodies will be absorbed out, precipitated out, and then the remaining supernatant will still have the antibodies that recognize human antibodies, okay, the antigen of concern. Okay. So expose it to the corresponding antigens of unwanted reactivity, precipitate out that unwanted reactivity, and then you'll still have in the supernated the activity that you are targeting. Okay. The precipitin test. The normal alpha human serums, or anti-human actually, this is another one of those things where alpha is used. You've been in science for several years now, so you know that scientists like using Greek symbols. Okay, we got your epsilon, we've got our omega from last semester. We have alpha here, but alpha is also used by immunologists as a symbol for anti. Okay, so don't get confused, because we had alpha, beta, gamma last semester when we were talking about optics and physics, but that alpha is different from this alpha. Okay, so that's the one thing about being a generalist. When you understand different disciplines, sometimes they'll use some of the same terms, but they mean very different things, and that's one of the things you want to keep in mind. Otherwise, it gets confusing. It's like, wait, why is this the fast ray? What, the refractive index? No, not at all. This alpha is being used to symbolize anti. So anti-human serums, which means that serums which were made against human serums. Okay. The normal anti-human serums used in forensic laboratories to determine whether or not an unknown stain is human are normally made by injecting whole human serum into a rabbit. Okay. So back to that idea. In the lab, you'll get a little manila envelope. Typically, I don't know if they still use manila envelopes, but it'll be your kit for doing your species of origin testing. It'll contain several vials of different animal serum, and then it'll also contain the same number of vials of antiserum against the series of animals. So I don't know what animals they have this year, but let's say, I've been saying human, cow, pig, cat, dog. Might not be all those. Human's definitely one of them, though. You want to be able to detect human serum. So if you have human serum, cat serum, dog serum, etc., then you will also have anti-human serum, anti-dog serum, anti-cat serum, anti-cow serum, anti-pig serum. Okay. So you have basically reagent and control, like a standard for the serum of interest. And what you will see also is that for the antiserum against those particular animals, well, they had to inject cow serum into an animal, so it might be rabbit anti-bovine antiserum. So what happened with that was it's anti-bovine, so it's against cow. They took cow serum and they injected into a rabbit. So when you have an animal anti-other animal, there have to be different animals, okay? Animal anti-other animal. The first animal is the host animal. The second animal is the animal that the reagent was made against. So some of the examples it says sheep anti-human, might be goat is is also used, anti-bovine, rabbit, anti-dog, let's say. Okay, so in all of these examples, the first animal was basically the host animal. It was the factory for making our reagent. So we took blood out of a sheep, which had had human serum injected into it multiple times, so we can get our reagent coming from the sheep against human serums. Okay, so this is host animal, and this is a, I guess, target animal, you might say. You're creating a reagent. Creating a reagent in the host animal that will recognize biochemicals in the target animal. Okay, that's the terminology that's used. So you'll have a series of little snap cap tubes that has animal, anti-other animal, but you'll also have standards because you need to have human serum. You need to have bovine serum, dog serum. You're going to test this reagent with this control. You're going to test this reagent with this control, etc. But you also want to make sure that this reagent is not going to give you positives for all of them. Okay? The test works well if this reagent gives you the positive for the human, but gives you negatives for all the other animals, right? That's what you want. Because if this reagent gave you positives for all of them, I don't know what I have. Might be human, might be cow, might be dog. What's wrong here? The reagent's not working well. Not a good reagent. Okay. So ideally, your reagents will only give you a positive for the target and a negative for all the other animals that are in that group. Okay. That's the goal. But you'll be testing those things to make sure there's no cross-reactivity. Okay. You want to verify that the reagents that you're given in your little packet do not give you cross-reactivities with the other animals. Okay. The resulting serum will react with a whole range of human serum proteins, because if you think about it, human serum's got a lot of stuff in it, right? It's got all the stuff in it, it's got all the antibodies, but not just antibodies, it's got other biochemicals, hormones, other kinds of proteins, some enzymes. You've got a lot of things in your serum. All that's getting injected into that rabbit, sheep, goat, whatever. And that poor rabbit's, all this weird stuff is in my circulatory system, so I'm going to be making a host, the rabbit's making a host of antibodies against all these different things that have been injected into it. And as a result, you'll get what's called a many polyclonal antibody reagent. Okay. The stuff that you get in the lab will be polyclonal, because we can't afford monoclonal. So I'll talk about what those different things are. Okay, so most commercially available anti-human precipitin sera. This is Dr. DeForest was showing a shotgun anti-sera, because shotgun meaning it's going to, like a shotgun can spray out all those different pellets, and hopefully it'll, I don't know, if you're trying to shoot a clay pigeon, it'll hit, some of those pellets will hit the clay pigeon that you shot into the air, but a lot of the other pellets will just be flying off into space and not hitting the target. So the whole idea is the shotgun precipitin sera, they're just making a whole bunch of things, and hopefully it'll work well for the thing you're targeting. Okay? They react with a whole range of human serum proteins. Okay? Protein-specific reagent sera can be produced by isolating a single protein. So this is more energy and effort. Polyclonal, I'll just take whole human serum, put it into my syringe, and inject it into the host animal. And so a whole bunch of things are going to the host animal. It'll take more energy if I say, okay, I want to isolate just these particular IgGs. So now I've got to do some kind of, electrophoresis or some kind of, way of separating
a single set of target proteins away from all the other things. So that's got to, that's several layers of analytical work. And then I'll take my purified, smaller subset of biochemicals from human serum, and I can inject that into an animal, and the animal will probably, it depends on what you're injecting into the animal, but even if you inject a single human protein, let's say, into, let's say, the host animal, let's say it's a rabbit. So you isolated a single human protein, injected it into the animal. The animal is still going to be making antibodies against, if my fist is the analogy of the human protein injected into the animal, the rabbit might make an antibody that recognizes this part of the protein, that part of the protein, this part of the protein. So it's still polyclonal, but it's more specific. As opposed to polyclonal, it recognizes this protein, another protein, another protein, and a different protein. Okay? So that's what we mean by specificity of the reagent. It's possible for it to be a single pure material, but it's still recognizing different epitopes, different parts of that single protein, or it might be so polyclonal and not as specific because it's recognizing many epitopes on many different proteins that have been injected into the host animal. So you could, take that serum and it'll precipitate a smaller number of proteins that are inside the human serum, but it'll be more specific. So here's a little diagram of poor little guinea pig over here. It's being injected with this antibody, antigen. This is the antigen. This looks like a string of colored pearls, right? This is our antigen. It gets injected into the guinea pig. The guinea pig says, well, not mine. Okay, well, not literally, but the guinea pig says, its body, its immune system says, foreign substance, time to make some antibodies. And so now you see inside the guinea pig's blood, not only is the antigen there, but also antibodies, and this particular antibody has recognized this epitope of this antigen. And then what happens is the guinea pig gets enough of this antigen injected into it, and it makes lots of these little antibodies. And then after a while, you take a vial of the guinea pig's blood. That's what you have over here. And you've already removed the cells. In the serum will be the antibodies that target this antigen. Anti-P30, okay, so a little preview of physiological fluids analysis. Anti-P30, what is P30? P30 is actually equivalent to prostate-specific antigen. So this is something that the men will have, prostate glands. Women don't, okay. P30 is actually prostate-specific antigen. But when George Sensabaugh discovered it, he didn't know that it was prostate-specific antigen. He called it P30 because it was a protein that had, I think the approximate molecular weight was around 30,000, and they separated out these different things by molecular weight. Anti-P30 is an antiserum, against prostate-specific antigen, also known as P30, developed against human seminal fluid. Okay, so. Poor little rabbit, right? I know! And the looks on your face like, oh. The rabbit gets injected with human seminal plasma. Okay? It sounds like some kind of sexual abuse, right? But it's also production of expensive scientific reagents. So if you want to, and we do have anti-P30, we should have it in the freezer in the lab. It's one way of analyzing a seminal fluid stain. Let's say the person has a vasectomy. So now that we don't have sperm cells anymore, person should still have prostate-specific antigen, also known as P30, in their seminal fluid. So if you have a stain that seems consistent with seminal fluid, it's a sexual assault case, and you've taken an extract from a cutting from the underwear, the sheet, the clothing, but you don't see any sperm cells, then another test you can do is the anti-P30 test. You can see if there's prostate-specific antigen in the material and that's an indication that it is a seminal fluid stain after all. That particular test I'll talk about in more detail in the physiological fluids lecture. It has to be done with care because prostate-specific antigen should be in seminal fluid, but as men get older, their prostate glands tend to enlarge, and they're more likely to get prostate-specific antigen in their serum, where you don't want it to be. Okay, so it's one of the things that as guys get older, they might go to the doctor, and the doctor will test them for their PSA levels. And if they have a high PSA level, it's an indication that they might possibly have prostate cancer. Okay, so which means that if you're testing the material and you're doing an anti-P30 test, if it's human serum, which, I mean, you're not going to see very often unless it was a crime scene where the human serum was spilled over places, or let's say there's a situation where someone was stabbed and they're bleeding internally in an internal body cavity, and because time is passing by, gravity causes the blood cells to sink, and the serum is above it. And then as the person's shifted, this is like actual case stuff, you might get a serum stain coming out of the stab wound. Okay, but that's not common. That doesn't happen much. Usually people get stabbed and they bleed, and maybe they get medical assistance and they're okay. Well, I don't know if okay is the right word, but or maybe they're not okay. Okay, so it would be a strange situation, but possible, that you can get a stain. Is it serum or is it seminal fluid? Right, very different materials, and this is back to the idea of context is really important. What's the context of this evidence? Where did it come from? What kind of case are we dealing with? What do we think may have happened to cause a stain to appear on this particular substrate? And what kind of tests will we run as a result of that? Because if it's blood, then it's probably looking very different from seminal fluid. Okay, probably. So radium has semen specific, and what else will react with this problem over here? Let's see. Resulting antiserum will precipitate proteins and seminal stains. This reagent is non-semen specific. So you might have situations where, like I said, you have some PSA in serum, and you'll also get a positive reaction. And in fact, by the time you if you have the opportunity to test your seminal fluid stains with anti-P30, you're going to be doing the similar kind of Ochterlony type test. You're going to take an extract of the seminal fluid stain, and you're going to put it into a little well of the Ochterlony plate, and then you're going to put across from it the anti-P30, and they'll migrate in the gel, and if you got a positive, you'll see a white precipitin band. Oh, okay, so the last thing I talked about was, if you took whole human seminal plasma and put it into the rabbit, then you'd get all these different things. On the other hand, if you purified P30, P30 purified away from the other components of human seminal fluid, then you have a more specific reagent that will react with P30 alone. And like I said, the caution you have to consider with that is that if you're dealing with serum from a man who had prostate cancer, so he's got PSA in his serum, which most men, you don't want that, okay? Then you might have a concern with that, okay? So it's not like 100% for seminal fluid testing, okay? So it's pretty useful. Anti-human hemoglobin serum in a similar fashion. I mentioned this at the at the end of the testing for hemoglobin, that if you could get an antibody that recognized human hemoglobin, then not only could you confirm that it's blood hemoglobin, but you can confirm that it's human. But like I said, this is not done very much because, you know, there are other ways of testing for these possibilities using DNA methods. Okay. So monoclonal antibodies, which I've alluded to before, and finally I'm going to talk to you guys about how it's made. Antibodies produced in the conventional way, the polyclonal method, can vary significantly from host animal to host animal. Because back to that idea, if you own that company that's making these reagents, maybe you have these 5 rabbits into which I will inject human serum, and then I have these other 5 rabbits into which I'll inject chicken serum and cow serum, etc. Okay. But when it comes to those 5 different rabbits, their immune systems might react slightly differently to the human serum that's being injected into their body. So, you know, rabbit number 1, its serum might work really well, but rabbit number 2 might give you some cross-reactivity with, you know, other animals. So you don't always have the kind of specificity that you want from the different animals that you're using as your little factories for your reagents. Okay. For more specificity, you can go to a more costly method of making monoclonal antibodies. Okay. So, how did monoclonal antibodies come about? Well, hybridoma technology. So what are hybridomas? Hybrid means you bring together 2 different things, right? Hybrids. And hybridomas are cells that are a result of fusing 2 different kinds of cells. Okay. So a hybridoma, the spleen cells of an immunized animal are fused with a cancer cell known as a myeloma. You get a hybridoma when you fuse these 2 different kinds of cells together. The spleen cells of an immunized animal, this would be the host animal. So let's say the rabbit is an immunized animal. You've injected human serum proteins into that rabbit. You got to sacrifice that animal now. You're going to take its spleen out and take its spleen cells and then fuse it with a myeloma, and you get a hybridoma. Why am I fusing it with a cancer cell? Because cancer cells, they grow like crazy, right? So you can start off with just a few of these hybridomas, but because they're cancer cells, as long as you're putting them in a nutrient-rich, you know, tissue culture flask, which nutrient-rich means it has food, the cells can eat and reproduce. And I used to do tissue culture, like 30 years ago. You would put in like a few cells into a tissue culture flask. You'd put it in with all like a nutrient-rich broth, and then the next day you'd go back and, oh, now I have a hell of a lot more cells in there because of the cancer type reproduction method. It makes a lot more of those cells. Because they're hybridomas, now you're making a lot of the cells that contain the antibodies of interest. But we're not at the point where we've got monoclonal yet. Okay. So yeah.
Sorry, can you fuse more than one cell?
Don't say sorry.
Because you're about to start something here.
No, but it's okay. If I've stopped and said, hey, you raise your hand, I'll take a question. You don't have to apologize, is what I'm saying. That article is saying mostly women tend to apologize too much. Sorry, you know. So I mean, I do it too. But then I would encourage you to think about
break
it.
the habit.
You don't have to apologize, is what I'm saying.
Can you fuse more than one cell together, or is it? I mean, sorry, more than 2 cells together.
Did it again.
I did do it again. I didn't realize.
Sorry.
Can you fuse more than 2 together, or can it be 3
It
or 4?
sounds like you're talking like Frankenstein technology here. Frankenstein
I
stuff.
was just wondering.
I don't know. I don't know if you can fuse together more than one kind of cell.
And, like, what would happen if you did?
When you put little electrodes over here.
Yeah.
Okay. I don't know. Okay. So cancer-like cells are immortal, and it doesn't mean the individual cell lives forever. The concept of having these tissue culture cells be immortal is back to that idea. In my tissue culture flask, I seeded with a few cells of these cancer-type hybridomas. They've reproduced to make a lot of cells because I provided nutrients in the broth that they're growing in. And what will happen is, if I need those cells for experiments, I would just, spin them down and then take the cells and, do an experiment with them. But if I just needed the tissue culture line to keep going, I would, after a while, the cell gets overcrowded with cells. I mean, the flask gets overcrowded with cells, so I'll just take a little bit of that and put it into a fresh flask with broth. And I have another seeded flask that is a little home for making more of these hybridoma cells. So immortal implies that it keeps reproducing, it keeps making more cells. As long as you're providing nutrients, those cells keep splitting, and that's like the same idea. That's why people have tumors, cancer tumors, because they just are uncontrollably growing larger and larger. Okay, you're making more cells than is healthy. So that's what is meant by immortal cell lines, not individual cells living forever, like in some kind of supernatural weird movie or something like that. It's that the cell line can be kept going on, and as long as you're seeding it into a fresh flask with more broth, they have these tissue culture cell lines that have been alive for decades and decades. So I've been doing this kind of tissue culture stuff since, I think, like the 50s. I think the Henrietta Lacks. I don't know if any of you, I haven't had a chance to see that movie, but there's a book, there's a movie. Henrietta Lacks she had cancer, I think it was in the 50s. Doctors took her cancer cells and they realized that they could make, basically hers was I think one of the first tissue culture cell lines that came from her cancer tumor. And she and her family didn't even realize that her cells were being used to make this immortal line of tissue culture cells, which, these days, HIPAA, privacy rights, you have to be aware that, what medical professionals are doing with your samples and privacy with respect to the results from those samples. But it's an interesting case in terms of the development of science and sometimes how it's unethically used to help people. Interesting enough. Okay. So you have your spleen cells from your rabbit that got injected with human serum. So those spleen cells are still making lots of different antibodies. You fuse them to myelomas to make hybridomas, and now you have this tissue culture cell line. And then you can, you can basically pick out a few of these cells that are only making certain antibodies and continue your tissue culture cell line so that you have a monoclonal antibody that's far more specific than the polyclonals. Okay. So the cells proliferating in the culture secrete the desired antibody are isolated, so you can separate them off from the other things, and then grow them in more tissue culture flasks, and then basically you started off with an animal as your host animal as your production facility, but moving forward for your monoclonal antibodies, your production facility would be flasks in which the hybridoma cell, the isolated hybridoma cells that target the exact thing that you want are growing in these flasks. Okay.
So when you produce new ones, they are
new what?
Sorry, new.
When you produce,
it comes naturally. I'm sorry. When you produce new cells, right? After having them keep multiplying, are they? When you say like isolated, like are all of them like the new ones?
Okay, so let's say you start off over here.
Monoclonal.
You've got your first flask of your first hybridomas have many different kinds of antibodies. Let's say each cell contains lots of different, all the different cells in your flask contain all kinds of antibodies in them. Okay. So after you've grown some of those hybridomas, you can use some biochemical methods to choose, let's say, just one of those cells that targets one epitope of the antigen of concern, and take that one cell and put it into a fresh tissue culture flask. And so instead of having, it's like a weird analogy, instead of having everyone's family living in one flask, and there are a lot of different people, I'm just going to take that one cell, put it into a separate flask, and now all that diversity is removed, and in that one, the flask that had that one cell with the nutrients in it, it'll divide, and all of those will be like identical, not even twins, identical multiplets.
Right, so like when you have the ones, the big family, do
That
they all
yeah.
come out, how do I say this? Do they all come out diverse? I mean.
Yes, yes.
And then you would, so some of them could have multiple sides, like 5, so this one has 4, this one has 3, this one has 1, and you take the 1, and then you multiply that?
Yeah, that's basically the
Is that
idea.
what you're doing? Okay.
If the original spleen cells will have lots of different things in them,
Yeah.
okay? You fuse them with a myeloma to get your hybridoma. So you have a whole bunch of different hybridomas in your tissue culture flask,
Okay.
okay? And some of them, like this one hybridoma makes lots of this antibody, this other hybridoma makes lots of the other antibody, and that's what I meant by like a family of different things.
Yeah.
It's sort of like that original flask is like the polyclonal flask. And then you pick out one of them that targets a specific antigen
You want.
epitope, and you grow that one. And now you have a lot of a thing that's much more specific. Okay, so so this part, the isolating it, is really important. That is the part that makes it monoclonal. If you didn't isolate the one thing of interest, then you still have a ton of these different these hybridomas, which recognize lots of different epitopes of different antigens. Okay, so if you just isolate, pick one that you want that can actually target the thing that you want it to target, and grow lots of those, then you get your inexhaustible source of highly specific antibodies. Okay, in flasks, growing over and over again. So this is another little cartoon. You've got your poor little mouse now. It's like, oh. Yes.
How do you fuse the cells together without like destroying it?
When you're doing those kinds of things, you're actually playing around with the cell membranes. Right? So you're not like we think of fusing as like you did the fusion exercise, hot plate, solid materials are melting. So this is an instance when we say fusion, it's more like Asian Latin cuisine. It's like you have these things together, but when we're talking about cells, we're not heating them up to fuse them. We are playing around with the cell membranes so that they can become a Frankenstein cell, basically. That's what we're doing. Yes. Okay. So we've got our poor little mouse over here, or rat. Sometimes rat, like I said, rat, mouse, all different kinds of animals. Don't tell PETA, right? Because for the ethical treatment of animals, it'd be like, oh. They will storm into like animal facilities where they're doing this kind of stuff. So I know, so the poor mouse is getting the injection of, let's say, human serum, and you've got your antibody-forming cells. Remember, it's a spleen. So after we inject this poor animal with human serum a few times, then it's sacrificed. The spleen is taken out. Spleen cells are fused with the tumor cells, okay? And it's kind of, I don't want to say cute, but here you have your hybridoma that has got like, it looks like a little feet, right? But that's little antibodies. It's showing that these cells are producing these antibodies. And I think it's maybe a little misleading. I don't know if they're necessarily sticking out of the cell membrane like the way you see over here. Okay, but so you got tissue culture cells, and these are also, once you make your hybridoma over here, then what it's showing you is that you've got this going over here. You've got your flask that's got lots of different hybridomas that are making lots of different antibodies. You screen, and you're not actually taking tweezers, you know, but you get, let's say, a single cell that you know is able, and you could probably, I would say, you take this cell and you reproduce it, and then you test it, because you're not going to take one cell and test it and then it's gone. You take that cell, you reproduce it, and then you take a sampling of that those cells to see if it can target the desired species, like human species, and do it specifically. Then you make lots of them in your flask, and monoclonal antibodies isolated for cultivation. So you're not using cells like when you get your little kits in the packet. It's not like it's filled with cells. They take the cells and they basically pop the cells, and you know, they separate the antibodies from the other things that they don't want, and then they sell it to you for a lot of money. Okay. That's basically the, you know, starting from the poor little, you know, rodent over here to monoclonal antibodies, hundreds and hundreds of dollars or thousands of dollars.
Really?
Oh yeah. You know, if you have an opportunity to invent or come up with some kind of scientific reagent, then cha-ching, you know, you can like retire, you know. And then hopefully you call me up and say, hey, I took that idea you told me about. Now I'm a millionaire in a mansion because I'm selling this reagent that I'm selling for, you know, thousands of dollars, and people will pay for them, you know, because scientific reagents and equipment can be very expensive. You have a question? No? Okay. Yeah, science. That's why running science labs can be very expensive. I'm about to send off, I'm having trouble with my Doppler system for ballistics testing. I'm about to send off an $800 little box and a $500 cable back to the company so they could troubleshoot it.
The cable and the box?
Yeah. $1,300 altogether is the value of these little things. I need them to work, right? So that's what I do. DNA reagents, those kits cost thousands of dollars. Like, you know, lab pay like, you know, $3,000 to $4,000 for a kit in a box like that. Okay. So yeah, but it's not because, I mean, I would like to think it's not because people are, I mean, yeah, I guess there's people in the corporation like, yeah, you know, making lots of money. But it takes energy and effort to make these things. And if you can make something that is highly targeted and extremely good at doing what it needs to do, then people will pay more money for it. And maybe the idea is that it took a lot of effort for you to make that. You had to screen through things. You spent years making this anti-cancer drug, for instance, that, so, you know, you want to make back some of the resources that you used up. Including time resources, you know, you had to pay rent, you had to like send your kids to school or whatever. So, you know, your company, the expenses you put in, yeah, I'm going to charge several $100s for this thing, so that to make back the money for, you know, what I invested to make it. So titer. So I alluded to the term titer before, T-I-T-E-R. It can have basically, it's an indication of the strength of a material or its ability to cause an immunological reaction. But it can refer to two different things. It can refer to the concentration of antibody, or it can refer to the concentration of antigen. It depends on the kind of test that you're doing. So that's why it's a little bit different over here. Now, in species of origin testing, if you think about the actual way you're doing a test, you're stain on a sample. You might not have a lot, okay? You cut out a small portion of that stain, you put it into the tube, you put some sterile water into that tube to extract the serum that was in that blood, and so now that's in solution. But you have that's your limiting reagent, not even a reagent, that's the limit in your sample. You don't necessarily, you might have a huge sample, pool of blood, or you might have like a tiny, tiny stain on someone's clothing. So that's what you're limited by. Reagent, aside from the fact that it might cost lots of money, you should be able to get plenty of reagent. So you're not limited by the reagent. So when we're talking about titer with these kinds of tests, we don't want to dilute our standard material. We don't want to dilute. We want to create dilutions in which the reaction will give us a positive. Okay? But what are we diluting? Okay? In this particular test, we're diluting the extract of the sample. Our reagent remains as it is not getting diluted. So this is another important thing to keep in mind. In your little packet that you receive for this exercise, you'll have your reagents, you'll have your standard serums. You'll be diluting the sera, you will not be diluting the antisera, which means that when you run out of this, there's not left to test more. Okay, so you want to be careful, but you can dilute these. And how much you're going to dilute them? Well, these reagents were made to work with a particular dilution, target dilution of a standard sample. Okay, so what is it? Let's say, and I don't know the exact, I don't remember, they haven't told, the technicians haven't told me the exact source, but let's say we've got sheep anti-human as a reagent, and this reagent, when I purchased it from the company that sold it, they told me that this reagent will work with a 1 in 1,000 dilution of human blood. Okay, that would be the titer that I'm working with, which means that if I want to do a control, I'll take known human blood, I'll dilute it 1 in 1,000, which means 999 microliters of water with 1 microliter of blood, diluted 1 to 1,000. The total is 1,000, and 1 of that 1,000 is blood, the other is water. Okay, I've got a 1 in 1,000 dilution of human blood, and that is what this reagent was designed to give you a positive with. So they typically tell you these things. You have titer for precipitin reactions, and you have titers for the agglutination reaction. And with the agglutination reaction, you are basically figuring out like how much antiserum can I add to how many cells. So you are actually looking at the, remember I told you that if you have a cell prep that's jam-packed with cells, and you put a drop of that onto your slide, and when you look through the ocular, your microscope, you just see like a ton of cells. If you were to add your anti-A to that, even if they were A cells, you might not easily see agglutination because you've overwhelmed the antibodies with too many cells. Okay, so titer, when we're talking about agglutination reactions, refers to how much can I dilute the cell suspension in order to be able to get a positive result. Okay. So let's see. Titer is defined as a unit of analytical detection of a substance. Analytical detection meaning that I can get the result that I'm looking for, which would mean a precipitin reaction. Okay. Which also means that, and as you're aware of, and I know we'll close off with this, I'll probably come back to this next week. Instrumental analysis, you learned a limit of detection. It meant that the cocaine might be in that solution, but the concentration is so low that my GC mass spec does not detect it. The signal to noise ratio, I'm not getting enough peak height to confirm that the cocaine's in there because the concentration is below the limit of detection. So the same idea with this kind of thing where the thing you're looking for might be there, but if the concentration of either the reagent or the thing you're looking for is not within the analytical detection zone, you might get that false negative. Okay, so those are some things to think about. So I've already mentioned titer. can refer to antibody dilution or antigen dilution. With the precipitin reaction, it's the highest dilution of antigen that will give a precipitin ban. Over here, when we talk about that, the blue anti-A, I think, and the yellow anti-B that you guys had in the refrigerator, for an agglutination reaction, we speak of the titer as the highest dilution of the antiserum that can still agglutinate the cells that you have. Okay, so the definition is a little bit different, and I will leave you with that time. Let me know if you're interested in the ABC exam, and I will probably talk with Dr. Dychuk and decide on a date for that exam in the next few days.
Did you just post that stuff on Blackboard? Or it's been there this whole time?
It's been there the whole time. What I do with Blackboard is I do the copy from last year, throw it into the new year, and then I start editing for, okay, the exam schedule is different, the homework thing is different. So it's a lot easier than repopulating a new Blackboard stuff. So that has been on the Blackboard site.
Yeah, I was doing the extra credit last night, and then I saw it, but I saw it there before, but it was just, I had time, so I was really like clicking through it.
Oh, because you wanted to learn?
I did.
Wow, I like that.
Yeah.
What?
That's a weirdo.